All right, good morning, everyone. I told you I couldn't be here today, so you're going to view this video and copy the notes into your composition book or onto paper. And as you go along, you're also going to be answering questions. So yesterday we covered ionization energy. It's how much energy required to lose an electron. And we also decided that on this side of the periodic table are metals, and metals can have a low number of valence electrons, so they tend to want to give away electrons because there aren't that many of them, so it's easier to give them away. And therefore, it wouldn't require a lot of energy to take an electron from a metal because it's already trying to give that electron away. Our nonmetals on this side of the periodic table have a high valence number. They're almost full. So it would probably take a lot of energy to remove an electron from them because of the fact that they are almost full and they don't want to give those electrons up. So we would say that nonmetals have a high ionization energy because it would take a lot of energy to remove it from them. And metals would have a low ionization energy. It wouldn't take very much energy in order to take an electron from them. So that's why we do our arrows like this yesterday in our bill. And so on this side of the periodic table, you have your metals. They tend to want to give away the electrons. So if you didn't write this yesterday, you need to write it. So since they want to give away the electrons, we would say on this side of the periodic table that they have a low IE or a low ionization energy. On this side of the periodic table, you have your nonmetals. They're almost full, so they do not want to give away those electrons. They actually want to gain electrons, so they're full. So to take an electron from them would take a lot of energy. So we say on this side of the periodic table that they have a high ionization energy. So as you go from this direction to this direction, from metals to nonmetals, this is high, and away from the arrow would be low. Okay, so let's do a couple of examples. You have sodium, aluminum, and chlorine. So I'd suggest you get your periodic table and circle sodium, aluminum, and chlorine. Draw your arrows. So for ionization energy, they actually get bigger going in this direction. And which one has the highest ionization energy? So you would follow the arrow, and whichever one goes with the arrow would be the highest. So chlorine would have the highest, because remember, my arrow shows the direction of greater or higher. Okay, so let's do another one. You're going to do beryllium, carbon, and oxygen. And we're doing ionization energy, so it increases in this direction. So which one, beryllium, carbon, or oxygen, would have the highest ionization energy? So we're looking for which one has the highest. So you're going with the arrow, so oxygen would have the highest. Okay, another one, we would have potassium, selenium, and krypton. And so you draw your arrows, but this time we want which one would be the lowest ionization energy. So we're looking for which one would have the lowest ionization energy. So you would go not with the arrow, because arrow shows higher, to go to the lowest ionization energy, the one that would not require a lot of energy. You would actually go against the arrow. So between those, potassium would have the lowest ionization energy, but that should make sense because it's on this side, and metals tend to want to give away electrons, so it wouldn't take a lot of energy to take them from them. So it wouldn't be a really big number or a high energy count in order to remove that electron. Okay, so now we want to look at this part here. Yesterday we said that that when you built your periodic table, that the higher numbers for ionization energy were at the top and the lower ionization numbers were at the bottom, which means that it wouldn't take a lot of energy to remove an electron from here at the bottom of the periodic table, but it would require an awful lot of energy in order to remove an electron from the top. So we said that this had a high ionization energy, and this one had a low ionization energy. Wouldn't take a lot of energy to pull from them. All right, so if you'll look, I've got a red magnet, an orange magnet, and a yellow magnet. And so which one would have a better chance of pulling or attracting that paper clip? And I'm hoping that you would say that the red one would have the best chance because there's nothing blocking the red. Okay, but in case of the orange, whoa, hello, the orange is actually being blocked by the red, and then the yellow is being blocked by the orange and the red. So the red one is getting the full, there's nothing blocking it. So there's like the full magnetic pull. But the orange one is being blocked by the red. So this orange one, it's not getting the full magnetic pull to the paperclip because it's being blocked. Same thing for the yellow. The yellow is being blocked from the orange and the red. So the yellow's like magnetic power is not like fully being let loose. I guess it sounds stupid, but it's being blocked by the orange and the red. So if we change that and we turn it away from paper clips and magnets, and we start talking about energy levels, if we say this is the nucleus, and we say this is the first energy level, and that's an electron, and this is a second energy level, and that's an electron, and this is a third energy level, and there's my electron. If I were to ask you which energy level or which electron has the greatest, remember the nucleus for the record is positive and all of these are negative. So which color up there has the best chance of attracting that proton that's in the nucleus? Well, it would be the same answer. It'd be your red energy level, or your red magnet has nothing blocking it. So there's nothing blocking that negative electron to being attracted to that positive nucleus. Remember, this is a nuclear charge, so there's nothing blocking it. Second energy level is being blocked. So this orange electron, or this orange second energy level, is not getting the full power of the nucleus because that red is blocking. The yellow is also not getting the full power of that positive nucleus because the orange and the red are blocking it. So instead of blocking, in chemistry, we call that shielding. The yellow one is being shielded by the orange and the red. It's not getting the full power of the nuclear charge or that nuclear power. The yellow is also not getting the full effect of that nuclear power. So if this was an energy level, this would be the top of the periodic table. It would take a lot of energy to take an electron from this first energy level. Because of the fact that it's so close to the nucleus, there's a very strong attraction. It would be a little bit easier to take an electron from the second energy level because it's not getting the full power of the nucleus, so there's not such a great strong hold on it. It would be easiest to get this last electron because the full power of the nucleus isn't that strong, so it'd be easier to get this electron versus the others. So this is why the arrow goes up. The higher you are on the periodic table, the closer those energy levels are to the nucleus. Therefore, it's harder to take that electron. The further you get away from the nucleus, you have shielding or blocking. And so it's going to be easier to take this electron from this energy level because it's not getting the full power of the nucleus because these other magnets or energy levels are in the way. Okay, so if we're going to write something, we would say that it's actually hard to lose up here. It would be hard to lose an electron because there is a strong attraction to the nucleus. Remember, you can pause this anytime to write this. And then as you get further down the periodic table, we say there's a low ionization energy. It would actually be easy to lose an electron because there's a weaker attraction. Because of that, there's a weaker attraction to the nucleus because that's shielding or they're being blocked. So let me read my handwriting. It's easy to lose the further you get down the periodic table because there's a weaker attraction because of that nucleus is being shielded. Those energy levels were being shielded from that positive nucleus. Okay, so let's do some sample problems. Let's do manganese. We'll do TC and RE. Okay, so you want to draw your arrows for we're doing ionization energy, so it goes the further this way and the further up. So we are actually looking for the highest ionization energy. So you would go, who's the furthest this way and up? So manganese would be my highest. Okay, so let's do another one. Let's do phosphorus. Sulfur and selenium. Now we are doing ionization energy. So again, I would draw the arrows. So we are looking for who is the highest, who is the furthest this way and up. So my highest would be sulfur. So remember, follow the arrows. The furthest this way and up is my highest ionization energy. It would take more energy to remove an electron from sulfur than all the others. Okay, another one. Let's do vanadium, chromium, and tungsten. Vanadium, chromium, and tungsten. So we are doing ionization energy, so I would draw your arrows, and we are looking for which one is the highest. So we're looking who's the furthest this direction and up. Which one has the highest ionization? Who would it require the most energy to take from? Would be chromium. Okay, let's do one more. Let's do SC, Y, and LA. So I want ionization energy. Who's the furthest this way and this way? But this time I want to know who's the smallest. So between those three, who's the smallest? Or not the smallest. Who has the lowest ionization energy? Who would be the easiest to pull an electron from? So what you would do was, if you want to go to the lowest ionization energy, who would require the least amount of energy, go against the arrow. Who's the furthest this way and over here? And so it should be LA. So it would require the least amount of energy. Remember, my arrows show highest. So if we want lowest amount of energy to remove an electron, you'd actually go against the arrows. Okay, so you will want to pause the video so you can write this. The last one is electronegativity. It is the ability to attract electrons. So this time we want to attract. So this was our last page. Metals, they don't want to gain electrons. They don't want to attract to them. They're trying to get rid of them. So they would have a low electronegativity. So our metals want to get rid of them. They don't want to attract them. Your nonmetals are almost full, so they really want to attract them. So we would say they have a high electronegativity. Okay, so when you're talking about this arrow right here, it would be easy to attract this part of the periodic table. So it would be easy to attract this part of the periodic table because there is a greater attraction to the nucleus. There's less shielding, so the pull is strong. So we would say that this has a high electronegativity the further you go up the periodic table. As you go down the periodic table, it gets harder to gain an electron due to shielding. The pull is not as strong to that nucleus, so they're getting blocked. So it's hard to pull an electron into these energy levels as you go down the periodic table, just because the pull's not as strong due to shielding. All right, I'm going to give you a couple of examples. Okay, so these are my 4 examples. And I would go to the periodic table, circle them on the periodic table. But remember, when we're looking for the highest electronegativity, it's the furthest this way and up on the periodic table. So make sure you're looking at it. We want the highest. And that would be vanadium. If I have these 3, circle them on the periodic table, it's who's the furthest this way and up. So silicon would be the highest. If I have this set up, it's whoever's the furthest this way and up would be the highest electronegativity, the ability to attract an electron. So that would be chlorine. But this time I want to know which one has the lowest electronegativity. So you would go against the arrows. Who's the furthest this way and down? And so phosphorus would have the lowest electronegativity. And don't worry, we'll talk about this on Friday as well. All right, circle out.